Hello, students. Getting into 8.2, the connections, the homework. Let me jump back a page here. Because 8.2b, it's a pretty short section in terms of homework. There's not a ton of questions. And so I've done 1 through 9 and 12 and 13. So let's take a look. So again, looking at the balances, which shape weighs the most and which one weighs the least. So as you take a look, remember, if, for example, one triangle is equal to 2 circles, anytime you see a triangle, you could replace it with 2 circles. And that visual is going to help a lot of students in your classes. So be able to kind of translate these problems into pictures if you need to. Okay. Now we can do the same thing here. Use a bar diagram to show your work when solving the following equations. So 7x plus 19 is 82, and 2x minus 5 gets you to 13. So again, if you were doing these, just to kind of show the setup for one of these, if you were doing like this bottom one here, 2x, and I take away 5 and I'm left with 13. So I have 13 and I took away 5, right? Here's 5 and I take that away, right? So 2x take away 5 gets you 13. So this entire chunk right here is 2x. Because 2x, when I take away 5, I get 13 remains. So what you've got now is a beautiful picture of 2x and how that is actually equivalent to 18. And since that's 2x, then you can come over here and say, oh, that's 2 of them. So there's 9 and 9, and that's where you have an x and an x, because x plus x would be 2x. And there's your bar diagram approach. Okay, you may want to also practice that magic box approach that I showed in my prior video, but again, that's completely up to you. This one says solve equations, so I'm not going to go through a ton of these. These are, again, the prerequisite for this class is algebra, but with what I showed, I think I've given you some tools. If you do see things that look a little weird, like with cube roots or square roots, it's okay. If you need to, call it a cloud, and then combine all of your clouds together. Here's a matchstick sequence. He used 590 matchsticks to form the last 2 figures of his sequence. That sneaky little bugger. So he's going to add 2 of these together, and your goal is to find how many matchsticks did he use in the last 2 figures. Okay, in each of them, like how much in one, how much in the other. Let's see here, 723 tickets sold for $3 student, $5 non-student. The benefit raised this much money. How many non-student tickets were sold? I think there's a similar question to this one up here on the previous page. Let's see if I can do, yeah, here we go. So let me take a look at this one just to kind of give an example. As some of you are like, hey, can you show a quick example of that? Oh, why not? Let's do one of these together, okay? Okay. And I'm going to show a couple different approaches, so hopefully you find one that you do like. I have 812 tickets sold for a total of $1,912. So I'm going to show the pure algebra approach. This is one you might have seen in a prior class. So I'm going to make an equation for tickets, and I'm going to make an equation for money. Okay, so I have types of tickets. I have student tickets and non-student tickets. Okay, so the student tickets I'm going to call S, and the non-student tickets I'm going to call N. And if I add those together, I have to sell a total of 812 tickets. Now the student tickets, when I get to the money, students are paying $2 each. So $2 for every student. And non-students pay an extra $1. So they're paying $3 per ticket. So now this is all money. And notice it says I brought in $1,912. And I have this relationship. Okay. Now, if I want to, I could go through and do something known as substitution, where I rewrite this as 812 minus N. And then wherever I see an S, right here, I just go plug that in. Now I have an equation that has nothing but N's in it, and we're good to go. Okay, that's one option. Another option is to use the elimination method, where I might multiply the entire equation on top by some value, rewrite that equation, and then add or subtract accordingly. So for example, that would look something like maybe multiply everything by 3. So now I have 3s plus 3n equals 3 times this, which becomes 2436. Okay. And now you could subtract these. I could subtract in either direction. I'll do the blue minus the red. So 3s's minus 2s's is 1s. 3n's minus 2n's is 0. And 2436 minus 1912 becomes 524. So this tells me that I sold 524 student tickets. I can put that back into the top one and figure out how many non-student tickets I must have sold. Okay. That's one approach. Could you solve this with pictures? And the answer is, oh, heck yes, we could. So what we could say is we have these two equations still, right? And here comes the fun, right? If you know that you have 2s plus 3n, these are like piles of money that came from these tickets, right? Think about what you have. You have s plus n, you have s plus n, and then you have an n, and they just happen to all be added together because that's really 2s's and 3n's. Then why don't we use this beautiful fact right here that an s plus an n is 812? Now notice all the money stuff together is supposed to be 1912, but if we use this fact, S plus N is actually 812. S plus N is another 812. I'm left with an N, and my grand total is 1912. Okay, so now what do? 1812 and 1812 turns out to be 1624, right? 1624 plus n gets me to 1912. So you could actually say, well, then 1912 minus 1624 has got to be n itself. And that gives me an 8. I'll do the traditional approach. I know some of you still prefer that one. Okay, this becomes a 10. This becomes an 8. And I get 288. 288 would be the number of non-student tickets, and put that back in, and I know the total had to be 812, and I can figure out how many there are student tickets. So there's the approach. Whew. Yeah, that's it. That's it. There's a couple different ways you could do it. What's another way to do it? I guess, I mean, if you're just thinking about it, this is the fun part of math, right? I know your algebra teachers would be like, no, you have to write it out algebraically. No, you don't, you dinks. Let's see here. So 812 tickets, right? If every single ticket was a student ticket, right? If every ticket was a student ticket, I would have $1,624. But you notice I actually have more than that, right? I'm off. So if I did $1,912 minus this and I get 288, it's like, well, I should have 288 more dollars. And you say, oh, well, wait a minute. Every non-student ticket is $1 more. Oh, then I must have sold 288 non-student tickets. Done. This is not unlike a bicycle or tricycle problem. These are ones that tend to be a little bit more at the elementary school level. Some people rode bicycles to school and other people rode tricycles, right? And you're like, okay, there were 812 kids and 1,912 wheels. And you're like, huh, okay. So if there were 1,912 wheels, and remember, some were bicycles and some were tricycles, you could start by assuming that, like every seat, this is a seat, and how many wheels it has. These are horrible drawings, by the way. So just take it. That's a seat, and that is a bicycle. See that? Yay, that's a bicycle. Horribly drawn bicycle. Just go with it. Just go with it, okay? So what we could do is we could say, well, I have 812 students. So if I just pretend I have 812 seats and I put two wheels on everything, then what you end up with is you end up still with 288 wheels. So what you do is you just go back and say, well, shoot, then let me come back up here and let's add another wheel on. And if I add an extra wheel on 288 times, that tells you there's 288 tricycles. And that leaves you with 524 bicycles. Okay, it's basically the same problem. $2 per ticket and $3 per ticket. 2 wheels per vehicle versus 3 wheels per vehicle. You see, it's the same question. Just yeah, the context is a little different, but it's exactly the same idea. All right, I hope you like one of those. Yeah, not critical that you have to do each one of them. Oh, let's hear. What else did I say? Through 9, 12 through 13. That has twice as many stickers. How many stickers must Matt give Dave? So they each have 120. Okay. And 9 and 12 and 13. The sum of the first two terms in a geometric sequence is 100 times the first term. Oh, interesting. See how they're playing that one there? That means you have to know how to form those geometric sequences like we've already talked about. So if the first term is A, and you're going to add the next term, remember the next term would be A times R, right? And that sum that we get is 100 times the first term. What? That is so cool. What a cool question. Yeah, so then I can just go through and I can say, well, wait a minute, how can I get this? Maybe I want to get all the A's on one side, or maybe I can think of multiplying or dividing by something to make it easier for myself, but create the equation. Just say it to yourself. The sum, that's addition, of the first two terms of a geometric sequence, write them out, that's your equal sign, 100 times the first term. So write it out, 100A. Then you go through and solve it. All right. Very exciting. Pretty cool. Yeah, I think that about does it. I think that about does it. And so yeah, your question is very similar. The outrage benefit concert. Okay. So many tickets, so much money. The one I did was $2 and $3. This is $3 and $5. It's a tiny little tweak. It really isn't that much different. It's just now, if you were thinking about the bicycle tricycle example, instead of putting one extra on to get to the next level, you'd put two extra on because the tickets are separated by $2 price difference, $3 to $5. Okay. All right. If you have questions on these, please let me know. I can make a separate video. I can meet up with you in Zoom or on campus in person if you prefer. Let me know and let's go knock it out. All right. Off you go.